Welcome to the blockchain hustle.
The mystical realm of the AI hardware, where chips are the currency and the supply is the king. It's a tale of intrigue, innovation, and a dash of supply chain drama that could rival a Hollywood blockbuster. Now, AI hardware has been one of the most trending topics lately. The demand for the AI chips has greatly outstripped its supply. Generative AI, with the likes of Chat GPT, has been a big catalyst in this demand. Everyone's tapping out prompts faster than you can say machine learning madness. And you know what this brings in? Data. Lots of data. And it's like hitting a jackpot in a digital data mine, ripe for monetization and for fueling the AI revolution. But folks, hold your horses. This newfound AI frenzy comes with its own fair share of challenges, or should I say pesky constraints. And the biggest one being the AI hardware supply and the pricing, especially on the AI chips. And it's not just the small players, even the big players are feeling the squeeze. They are jostling for dominance while the smaller ones are trying to find their place in this hardware hierarchy. So let's unravel this frenzy, peel back the layers, and get into the heart of the matter. Who's pulling the strings in this AI hardware space? What is the deal with the supply chain, supply demand dynamics, and the almighty dollar? And how much dough are we talking about here? And how can the little guys wrangle their way into accessing this coveted technology? But before we dive into the nitty gritties, let's take a quick crash course in the AI hardware lingo and tech. Now, semiconductor chips have been powering our everyday gadgets, from the smartphones to the supercomputers. But now the spotlight's on AI, especially on issues like the accessibility, pricing, supply demand scenario. And traditional CPUs and GPUs are feeling the heat. Now, the computing needs have evolved. The traditional computing was all about crunching numbers, sequentially processing instructions one after another. The CPUs ruled the roost with their speed and efficiency. And then came the GPUs, strutting into the scene with a parallel processing prowess, which was perfect for rendering those jaw dropping graphics in the gaming space. And then stormed in AI, machine learning, deep learning, and specifically generative AI, which just got AI out to everyone. And suddenly, computing needed a whole new playbook. AI's voracious appetite for data and complex computations just demanded a different breed of hardware. AI needs chips that can handle its complex matrix maths, juggle the massive data sets, basically specialized hardware that speaks its language, dances to its algorithm, and doesn't break a sweat when it is faced with those mind boggling matrix maths. Deep learning is driving new computational loads. And when the workloads change, the underlying hardware architecture evolves. Now, as I said, AI has different computing needs than the traditional ones. And to see how, let's get a little bit deeper into the matter. AI chips, also known as the AI accelerators, are basically chips designed specifically for the AI applications, especially deep learning. But what exactly do they do? Let's break it down. Now, deep learning includes two main tasks: training and inference. Imagine your AI model as a student in a school. Training is like hitting the books, learning new concepts, and practicing till perfection. It involves feeding the model tons of data, sifting through it, identifying patterns, and then making predictions basis that. Loosely speaking, we are training the model to learn. And inference is a phase where the trained model is now put to work. It's taking the exam. The model makes predictions or inferences on the new data which it may not have seen before. So, training is the model development, while inference is the model deployment. However, let me point out something here. Training is simply the process of fitting in a set of model parameters to produce a minimum error on a bunch of examples in a training set. It is not learning in the generic human sense. We use the term training just so that it relates easier to us. Now, general purpose chips are traditional CPUs. They can also do these tasks, but not efficiently enough. Why not? Well, as I mentioned earlier, the traditional CPUs were built for the sequential processing. And training, it needs to process massive volumes of data. And if we were to put in sequential processing onto them, that's going to take forever. We need something fast to train a model. So let's now meet the rockstars of the AI chip world. Start the GPUs. There are going to be quite a few acronyms out here. Now, GPU is a graphic processing unit. Now, these powerhouses were originally designed for gaming, leveraging those parallel processing to render those jaw dropping graphics. And over time, they have been especially customized specifically for deep learning. And now they are the go to choice for training those large language models, the LLMs. And NVIDIA leads the charge here as the gaming boss. The next one is TPU, the Tensor Processing Unit. Google's brainchild, the TPUs are tailor made. They started with specific AI as the focus. They're tailor made for AI with a focus on tensor calculations. Now, what are tensors? Think of tensors as dynamic data containers, more natural and a more intuitive way of processing vast and complex data sets more efficiently. And then we have the NPUs. NPUs are the neural processing units, more akin to how our actual human brain functions. They are custom built for the neural network computations, especially for power efficient inferencing. For example, you have Intel's Meteor Lake, Qualcomm's Hexagon NPU. They accelerate tasks like object detection, natural language processing, and a key difference between the TPU and the NPU here is that TPUs are specifically designed for deep learning, while NPUs can work across a wide range of the machine learning applications. Now, you have AI chips which are optimized for specific tasks of machine learning. For example, it could be for juggling large data sets for training or for inferencing, especially where they need to be optimized for the higher power efficiency, energy efficiency. Something which comes in pretty handy in the edge devices. Because you see, in the edge devices like your mobile phone, etc., power becomes all the more important, both consumption and dissipation. So it needs to be optimized there. Amazon has a training chip called Premium, and its inferencing chip is called Inferentia. And then you have further on specialized chips like ASICs, application specific ICs. You have FPGAs, the field programmable gate arrays, which are designed specifically for certain tasks. They're not those general purpose ones. And then architecture wise, some of them are digital, some of them are analog, and they come up with different trade offs like precision versus speed, or it could be power efficiency. Now, an important point to note here is that training and inferencing have each got different computing goals, and hence we need to select the underlying hardware accordingly. Training has a goal that it needs to train large number of data sets as fast as possible. And inference takes a single input and it pushes it through many layers of the network. So the metric of performance for inference is latency. That is the time it takes to push an item through the network and to get an output. How fast do you get that? While the metric of performance for training is its throughput. That is the volume of the training data per second that you can manage. So you see, you have different uh, goals, different metrics here. So you need to pick your hardware accordingly. And now we come to a few trailblazers shaping this AI hardware scene. The first one, NVIDIA, the OG trailblazer. Now, NVIDIA got itself an earlier seat on the AI hardware table by both luck and well timed strategic moves. Its gaming platform chips, the GPUs, they found a good fit with the AI computing needs. And it optimized them further for AI. And the AI hardware is not just about the chip, it's also about the network fabric, the memory, as well as the software development kit. It's a complete ecosystem. So, NVIDIA also acquired Mellanox Technologies, and that gave it an additional edge on the AI network performance. Plus, it has a very robust, well developed, mature software development kit, an SDK, to facilitate developers put together a holistic AI infra solution. NVIDIA has something called NIMS, NVIDIA Inference Microservices, which is a self contained software package that can be bought off the shelf or customized to specific needs. And all this gives the advantage of clients sticking within your hardware software ecosystem. It's like having a vertical garden. NVIDIA's customer base includes cloud computing giants like Amazon, Microsoft, Alphabet, and others, and also the Gen AI makers like OpenAI. A trend that we are seeing here is that as businesses are seeing Gen AI's impact, its benefits, etc., on various verticals like healthcare, manufacturing, retail, and others, these businesses are seeing an evolving need to make their own models and not just rely upon the model makers like OpenAI and others. And this is where NIMS will come in handy. Apart from NVIDIA, you have AMD, you have Intel. AMD has this MI300X data center GPU, and Intel's Gaudi 3 rivals NVIDIA's H100. And then you also have those tech titans turned chip makers like Google with TPUs, Microsoft with its Azure Maya, if I've pronounced it correctly, AI Accelerator, and Amazon with Trainium and Inferentia. They're all flexing their AI muscles and disrupting the traditional chip landscape. For example, Anthropic, which is the startup with Cloud 3, a competitor to OpenAI's ChatGPT, Anthropic is backed by Google and Amazon. And adding to this mix are some fascinating emerging compute architectures which are coming up. And this is coming through an influx of new players like D-Matrix, Untether, GraphCore, Cerebrus, Celestial, and others. It's a pretty exciting space to watch. Now, 2 points especially pique my curiosity in this space. The first one is the new compute architectures. And when I say the new compute architectures, they're not just the ones which I have cited earlier, but especially architectures like the neuromorphic models, which are evolving for addressing not just the computing needs, but addressing the computing needs with power efficiency, with data set efficiency. So you see, typically these all these large language models, these LLMs, they require a humongous amount of data sets for the training. And all this requires a lot of time, a lot of power, and we are just not equipped for that. And it is practically not sustainable. So we need to look into something which we can do a little bit more efficiently. So, overturning, for example, the traditional von Neumann model with the localized memories for computing units is one such architecture. And the second one is the new players which have come into this arena. And it's not just your traditional silicon players like your NVIDIA, AMD, Intel, and others. The new playing field has got the likes of Google, Amazon, Microsoft, who were initially customers. But now they're not just customers, they're contenders. They're reshaping the AI hardware landscape with their deep pockets, boundless ambitions. And they're not being constrained or dependent on NVIDIA and the likes for their AI computing needs. So that's a couple of good things that one can chew on. And that's basically the stuff about the AI chips, the tech, and the market. My next podcast will be on the costing, pricing, a peep into decoding those eye watering price tags of these AI chips. Not for the faint hearted. So we look into the questions of where are these high figures coming from, the high prices, and how can the smaller players get their hands on this AI power? So do stay tuned. Well, that's it from my side. Thank you for your attention and time. If you do have any comments or queries, I would love to hear them. You can reach out to me at minu@minusareen.com. My Twitter handle is minusareen, and my contact details are here. Of course, you can always leave a comment down in the comment box. So, till the next one, see you later. Cheers.